of galactic stars in the halo and orbit tracking survey, and as you know, the acronyms, your undivided attention, and I will let you know 3 minutes before and 0.
Okay, thank you. Yeah, I can't really take credit for the acronym. This was we didn't realize this at first, but Sebastian decided to send me an email saying we should call it mugshots, and then I found his old HSC proposal that is mugshots. So this is really Sebastian's acronym. But yes, my name is Zachary Hartman. I am a science fellow at Gemini Observatory, moving on to NASA Ames in the fall. And this is a awesome project that I started working on a couple of years ago with Sebastian and Mike Rich at UCLA. And so this is our survey looking for multiplicity of galactic stars in the halo and orbit tracking survey. So it feels weird for me to say it because I've only been in astronomy for a decade, but it really feels like astronomy has changed a lot in the past decade. And in particular, this plot on the left, which is just a simple HR kilomagnitude diagram from Gaia, I think kind of exemplifies this, because when I started my PhD 9-ish, 10-ish years ago, this was not the first plot I made. It was a reduced proper motion diagram was the first plot I made. And so now, with over a decade, we're now able to build this awesome HR diagram and see a lot of interesting structures in there. You know, you look at the white dwarfs and you see the double main sequence there. You see that the vast majority of stars within 100 parsecs, this is the 100 parsec sample from Gaia, selected for stars with proper motions greater than 20. You can see that the vast majority of these stars are M dwarfs, and Todd is going to be talking about those next. And then you can see one of the awesome features of this diagram, which I am particularly happy about because I'm a all binaries all the time type of person. If you look in the K dwarfs, as we heard earlier from other Zach's talk, you have this overluminosity effect from unresolved binaries, causing Gaia to see the combined light from both stars. And in particular, over the last decade, we've had an astounding amount of advancements in our understandings of star formation, and in particular, young stars and in stars in the solar neighborhood and the disk. But we're kind of forgetting something, and that's our old friends, the galactic halo, the subdwarfs below the main sequence. And in particular, these are extremely important, as we heard earlier today and saw in the great video in the plenary this morning, that these stars are traveling around the galaxy. With these stars, we can trace the dynamical history. And in particular, in the past couple of years, they've really gotten a lot of attention for tracking accretion events from Gaia Enceladus or the Sequoia. And additionally, they also allow us to track the chemical history of the galactic halo, or of the galaxy. And given these importance, you might think, oh, we should know how these stars form, but we really don't. We don't have a really great understanding of how star forming worked early in the galaxy and how what the environment was. Now, we've really started to figure out that it was probably metal poor, and we've been working towards improving our understanding of that. In particular, in 2010, Rostigave did a combined speckle imaging plus literature, spectroscopic and visual binary data, and mapped out what a sample of halo stars, solar type halo stars within, I believe, 250 parsecs, what that binary function was, and that's shown on the right over here as a function of period. You can see the population 2 of the halo stars has a peak that is closer or at shorter periods than the galactic disk. And a couple of years ago, Moda in 2019 did a similar reanalysis of a bunch of surveys and found that yes, the close binary fraction is anti-correlated with metallicity. So as you go to more metal poor stars, you have more closed binaries. But these, you may have caught a couple of words in there that may have sound like we aren't being complete. I said solar type a lot. And as we all know, and as we're going to hear in a couple of minutes, M stars are the most numerous star in the galaxy. And so to better understand the formation of the halo stars in general, we need to really include M stars in the galactic halo into this analysis. And in order to do this, we need to get a couple of different parameters. We need the period distribution of these binaries in the galactic halo. We need the eccentricity of those binaries. We need to know actually what the multiplicity fraction of the galactic halo is, because that's still not precisely determined. And Critically, we need binaries where we can determine the mass, because we really don't know what the mass ratio distribution of binaries in galactic halo is. We don't know what the mass luminosity relation or the luminosity function are. And so to do this, we need to find the binaries. And Gaia was huge in this. This is a picture of visual binaries that Gaia found, these wide binaries with separations larger than an arcsecond. But in order to get the full picture, we need to go and search closer. And that's where mugshots comes in. And so Sebastian, over the past 14 years, has been conducting a adaptive optics imaging campaign in collaboration with Mike Rich at Lick Observatory using the 3 meter there. And more recently, once I got involved, we started applying for speckle time at Gemini Observatory. And so we have been observing a large amount of stars. And in particular, Gaia has allowed us to expand our survey to the lowest mass M stars. In particular, using Gaia and doing tangential velocity cut at 150 kilometers per second, we've found about 1,100 stars within 100 parsecs that we can observe using Gemini speckled imaging. And in particular, I will note that this is not a complete sample. We are missing some stars due to Gaia not having the data. And so that is going to be a future project to work on, is finding those stars that don't have Gaia data and getting any data on those. And so we have these 1,100 stars. And so what we've been doing is going out and imaging them. So first one I want to talk about is the Lick Adaptive Optics Survey. We have 120 of those observed with Lick. I mentioned that Sebastian has been doing this for 14 years. So this is just the 120 within 100 parsecs. We have over 700 out to, I believe, around 250 parsecs, and all with proper motions greater than 250 milliarc seconds per year. And so I'm working on reducing those. I have about 400 reduced, and we just had an observing run this weekend. And so I have more to reduce. And so that will be my life in the fall. And we've been doing this using the Shimmer pipeline from Zavala 2022. And you can see that we are able to find these binary stars that are close in. I've been doing a couple different subtractions using different functions, and we're able to find these companions. And so one of the things, though, is that we want to get as close as we can and find all the companions within that separation range. And so Lick Adaptive Optics is really good, but it only goes down to about 0.1 to 0.2 milliarc seconds. So what do? We need to go to some place that is a bigger telescope and therefore we can get closer in. And so at Gemini, we can get down to about 0.002 or 0 to 20 milliarc seconds in the red filter, which is this 832 narrowband filter. And so we've been using Alpec and Zorro. We have over 230 observed, with a big chunk of those in the southern hemisphere, actually, which is great because Lick is in the north. And so we've been able to expand to the south. Mostly this has been band 3 time, which for those of you who have used Gemini is normally filler time, but it's been awesome because we actually get a lot of these stars observed, because we're just like, we have 500 targets, please observe any of them, and they do, and it's great. And so on the right, or on the left, I show the data products that we get from the NASA Speckle team, which is the contrast curve and the plot behind the reconstructed images. So you have delta mag on the Y, separation on the X, and so anything above those curves, any companions above those curves, we would detect. And so, and then we have the reconstructed images showing the actual objects. And so what do we get? Well, for the 340 that we have observed, we found 24 binaries that have been resolved using speckle imaging or Lick Adaptive Optics, and are closer than the limits of super wide, which is my wide binary catalog, which has a lower limit at about 2 arcseconds. We've detected 3 Gaia resolved triples and 29 wide binaries in the sample. And if you look at this plot on the right, or on the left, you can see that the red stars represent our detected binaries. The cyan points are, again, that sample. And then the gold points are what we've observed. And one of the key things that I've noticed in this plot, as it's been steadily being updated over the past couple of semesters, is that we're still not finding binaries that are actually down in this area, and that are down in this lower main sequence. And to me, this kind of indicates that we're not really finding a lot of the halo binaries, a lot of the low mass halo binaries, low mass ratio halo binaries. So we're finding potentially equal mass systems that are overluminous. So like these three red stars up here, they can potentially, they're equal mass systems that are overluminous. So they would normally fall down in this area, but they're elevated up because Gaia sees the combined light from two stars rather than just the one. But there's also been indications in past literatures that, past papers, that potentially that these galactic halo stars don't have a lot of low mass or high mass ratio companions. They're all almost equal mass. But so this is potentially something that we're going to look into and hopefully get more data and see if we can find those stars. So if I put these plots in a projected physical separation versus distance plot, you can see that we're getting down to the diffraction limit of Gemini. These are the red and blue lines over on the far right, far left. Then you have the cyan line there that represents Lick as the diffraction limit. Then you have the two solid red lines. Those are the limits of super wide at 2 arc seconds and 3600 arc seconds. So you can see all our wide binaries and resolved triples are in here from super wide. Everything below is from high resolution imaging. And if you take all of these stars and you look at only the ones that have been examined with speckle imaging and you calculate a multiplicity fraction from that, you get about 10.6% plus or minus 2. And this is actually pretty comparable to a previous result from Ziegler et al. Using RoboAO of 12.5, but this is now crucially including a lot more M dwarfs than what was in that sample. And so this is kind of where we're at right now. I just want to spend some time focusing on what's next and also some other work that is going on in our group. So this is just the 100 parsec sample that I'm working on. We have other people working on other projects trying to figure out the multiplicity fraction of the galactic halo. In particular, Melody Soniker has been doing a lot of work using HST and has a poster. So if you are interested in it, please go check it out. It's in the Mosaic building. And then also we have a former grad student who was in our group with Sebastian working on eclipsing binaries, Bakyeon Kim at the University of Edinburgh. And she's found 22 so far in her sample. And then I'm just going to leave this slide up here because I'm out of time and just say that we are not complete. We know we are missing close-in companions, and we know we are probably missing high contrast companions. And so we're looking forward to the next available telescopes and observatories that are coming online in great anticipation of what we can find. So thank you, and I'll take any questions.
Thank you so much for that great talk. All right. I have
Welcome.
questions. Yeah.
Okay, Rafael Reyes from Centro de Investigación en Astronomía, Santiago, Chile. My question is about the galactic halo and the binaries that you have. You said that they are already very low in number, but whatever you have, is there anything related to 0.8 solar mass object? Because if this is the case, then there is a possibility that it is actually the survival object from the population 3 stars. They got ejected, and they're saying that it might be existing in the halo of the galaxy. So if that is the case, then it could be a POP3 case.
Yeah, I haven't looked into like actually determining stellar masses, but just looking at the HR diagram, most likely, or the HR diagram that we have for this, most likely. So I'm happy to look into it, but I don't have an immediate answer for you. Hi, Elliot.
So given the distances of your targets, and I'm thinking about the upcoming Gaia data release. So given the distance of your targets and the parameter space with which the Gaia astrometry is going to be good, do you expect that to be very helpful in helping you detect some of the things that maybe have gone undetected in your thing, or do you think it's not going to contribute to it?
Yeah, so the question was, I forgot to repeat the last question. The question was that given that Gaia the R4 is coming out with all their astrometry data, how much of it do I think is going to be useful for the halo star population that we have? And I think it will be. I mean, one of the great things that we've learned over the past couple of years is that you have this close binary fraction that's anticorrelated with metallicity. So I expect there to be a whole bunch more close binaries. And so hopefully Gaia will be a huge help in that regard, rather than making me go and take 1,000 and more spectra on all of these things. So.
A lot of folks are getting a lot of speckled data and characterizing binary systems. I was wondering if you thought at all about and also there's been a lot of thinking about how to detect binaries through astrometric or Gaia parameters. I was wondering if you thought about approaching it the other way and defining the selection function empirically. Like you find some binaries and then you say, oh, what does this look like in Gaia? And would we have detected it given these classic cutoffs of like Rui, IPD, multi-frac?
Well, I'm kind of happy you mentioned that because it gives me an excuse to go to my backup slides. So I did look at it, and so with the Rui values and the IPD multi-frac, we detect a lot of them. For Rui, if we do a Rui cutoff of 2, we get about 15, and if we go with IPD multi-frac, we get about 10 or 11. Actually, the weird thing is that 0 are in the non-single star catalog, which I found to be kind of interesting. But we are looking. And actually, if you take all of that, if you take just those parameters and you say, okay, Rui greater than 2, IPD multi-frac greater than 10, they're members of the non-single star catalog. Out of the 1,100 that we have, we only see about 120 that should be binaries. Now that fraction goes up significantly when you use RV error, but the RV error also, I was just doing a straight cut on that, and we have very faint stars, and so that does not technically work with a flat RV error cut. So I don't believe that number. That's why I stuck with this number. So, all right.
Maybe. That looks right. Hi. Ready for something different? I'm gonna have